Good morning, everybody. Thank you for participating once again of the international seminars Global Rivers in the Anthropocene. It's my big pleasure to introduce today to our invited speaker, Professor Rashid Sinya. Professor Sinya is a professor of the Department of Air Science in the Indian Institute of Technology, Kanpur. He has a master's degree in applied geology from the University of Roorkee in India and a PhD in sedimentology from the University of Cambridge. Dr. Sinya is a top specialist in river geomorphology, sedimentology, hydrology, and hydrogeology. As I mentioned before, he's a professor of the Department of Civil Engineering at Indian Institute of Technology, Kanpur, where he created the Department of Air Science and was the founded head of the Department of Air Science. I can say that Professor Sinya is one of the foremost river scientists, not only in India, but internationally. He has produced a significant contribution on river dynamics, flood risk analysis, alluvial stratigraphy, quaternary research, and river health assessment and wetland studies in the tropics, with focus, of course, on India in many cases. Professor Sinya has more than 200 papers published and thousands of citations. He's a recipient of the Alexander von Humboldt Fellowship. He has been a visiting scientist and professor in a variety of multiple universities worldwide, in the University of Karlsruhe, the University of Potsdam in Germany, have been our visiting scientist in Brazil several times. He also received the National Mineral Award, the MER Award, and is a fellow of the Indian Academy of Science, Bangalore, and the National Academy of Science, Allahabad. Regarding his scientific duties, he also has been a member of the editorial board of different journals, such as the Sedimentary Research, Quaternário International, Air Surface Process and Landforms, Current Science, and several others. So for us, it's an honor to have Professor Sinya today. Welcome, Rashid. Thank you for accepting our invitations. Please go ahead. The stage is yours.
Thank you, Edgardo, for introducing me, and good morning, everyone in Brazil, and good evening to friends in India. It's an absolute pleasure to be talking today on the invitation of Professor Latrivesi, and he has been running a wonderful series on the global rivers in Anthropocene, and I'm happy to talk about the Indian rivers today and how they behave, how they look like in this period of Anthropocene. So let me start my talk. I hope you can see my screen well, and so I am going to start with a very quick introduction of the Anthropocene. Most of you probably know this already. We'll talk a little bit about how the global stature of the rivers are in the period of Anthropocene, and then we'll very quickly move to the anthropogenic stress on the Indian rivers, and I will try to illustrate various issues related to the Indian rivers through a couple of case studies. And some of the topics I have chosen for today is the impact of engineering interventions, for example, sediment dynamic, which is a major problem in many of the Indian rivers, both in terms of the excessive siltation as well as sand mining. I would try to cover, a couple of aspects related to river health of the Indian rivers as well. And then, as I said, I will use quite a few case studies and examples as we go along. Now, the term Anthropocene is now very well established in the Indian literature, although it was first introduced by Paul Crutzen in 2000. And even today, although we do not have a real consensus on the actual date of the commencement of the Anthropocene, but there is a general agreement in terms of the philosophy that this is the period when the humans have exerted a very major change on the natural systems. Uh, Two very commonly discussed dates include, for example, 1750 of Common Era and 1950 of the Great Acceleration in Technology. But then, as earth scientists, we all know that the impact of the humans on the natural systems, they date much, much before that. And there are very definite periods which are recorded in the geological history. For example, 14 to 10.5 K of the megafaunal extinction, 11.7 kilo years of the domestication of plants and animals, 10 to 5 kilo year of agricultural practices and deforestation, and then the 2 kilo years when anthropogenic soils have started to develop. This debate, of course, continues, but then, lots of people have already started looking at the Anthropocene and its impact on water cycle and on rivers and so on. This is a very recent paper by Bock et al., wherein he looked at the consequences of the human interference with water cycle. And as you can see, there's a variety of impacts one can think about, from the land conversion to to nutrient loading, to water quality aspects, and to the alteration of the ocean currents and so on and so forth. So there is a big variety. There is a big effect on the water cycle which the humans have made in the last several decades. In terms of the rivers, when you talk about a natural riverscape like this, which probably exists only in the paintings now, we know as geologists and as scientists that in a natural riverscape, the river runoff is primarily controlled by climate as a function of precipitation, evapotranspiration, discharges, and so on. And the sediment flux, sediment production and mobilization is primarily controlled by geology and climatic factors, basically. So, the hinterland characteristics, for example, and so on. Now, in the context of the Anthropocene, there are several questions which we have been asking, in terms of the impact of Anthropocene effects on the rivers. For example, how these fluxes of water, sediment, and biota have changed through time, particularly since the human imprint became strong. What are the major impacts of these changes, and then how can we mitigate these impacts? There has been a lot of work, a lot of literature on the impacts of river spin. Again, there is a very recent, more rather recent compilation by Martin Dwelling, who looked at what the different kinds of impacts any rivers would be expecting in the period of Anthropocene. Again, you can see that the impacts they range very widely from from the extraction of material from the rivers, water utilization, waterways construction, fishing, farming, and all of that stuff, and so on. And again, he very nicely put 6 different stages of the impact of river impact on rivers in the period of Anthropocene, starting from something like 15,000 years, where he looked at he said minimal effects, then 10.7 kilo years with minor effects, 9 kilo year onwards, we see a agricultural era, impact of agricultural practices on the rivers, and then 6.5 kilo years, we see a major impact on the rivers because of irrigation structures, and then 3 kilo years is a technological invention, the engineering era, which obviously continues all the way through 1800 CE and so on. And that's what we are. So we are today in a period of Anthropocene where any rivers or most rivers in the world are experiencing many kinds of effects, in terms of human interventions. In terms of the Indian rivers and Anthropocene, uh, these are just some of the effects which we have been looking at. Right from environmental flows to sand mining to biodiversity loss to water pollution, floods, and so on. And of course, I may not have time to discuss all of these today, but I will try to pick up as many as case studies and as many problems as we can in terms of the Indian rivers. So, what we have seen and observed that most rivers in India have undergone very significant human disturbance because of the growing demand of water. But then the problem we have been facing is that we are not able to quantify the quantum of disturbance because there is a lack of knowledge of a reference condition. So that's one problem. And then on the top of that, there are uncertain impacts of climate change in terms of rainfall variability, glacial melt reduction, meltwater reduction, and so on. So what is very clear, today that we need very effective river management strategies to reduce the water stress and economic development. And then, and many times these management strategies are contradictory to the ecosystem development or ecosystem, biodiversity, and so on. So the challenge before us always is that how do we strike a balance between the human needs and the ecosystem protection? So let me run through a couple of case studies which have been done by my students and my other colleagues, across the country, and then to pick up each and every problem as we go along. So let me first pick up the first problem, and which is again a very major problem of flow reduction because of the anthropogenic interventions on the rivers. And this is a case study which we did, in the upper Ganga River, and you can see there are two major tributaries of the upper Ganga, Bhagirathi and Alaknanda. They both meet at a place called Devprayag, somewhere here. And then from this point onwards, this river is actually called the Ganga. So the aim of this study was to look at what are the hydrological implications of the increasing reservoir-induced and climate-related stress on the system. And in particular, we focused on a very major and a very large infrastructure here, which is a very large dam at Tehri, and which was constructed around 1995. And therefore, we divided the period of our analysis into two periods, 1971 to 1995. We call this as a pre-intervention period, and then the 1995 to 2010, which is the post-intervention period, and so on. Now, so if you look at the overall, structure of the flow duration curves of the rivers at different stations, so all of these are different stations in the green color. They look pretty normal, because this is the integrated response you are looking at. I would also like to draw your attention to the fact that there are already a couple of dams which are existing on the river, shown by the brown triangle and the yellow triangle here. Some of them were constructed before 2010, and some of them came later after 2010. But then they still might look a few in number. But if you look at the planned hydraulic structures in the next couple of decades, I think the scenario changes completely. This is absolutely crazy to see this kind of a map here, where we are planning so many small and large structures on the river systems, and the impact of which on the hydrological regime of the river is still quite unknown. So let us focus on this particular study, where we looked at the integrated response of the climate stressors as well as the hydraulic interventions. These are the two basins I just talked about, the Bhagirathi and the Alaknanda. And again, the data for rainfall this is for pre-95 period, and this is for post-95 period. And again, we have plotted here the annual rainfall data. And also you can see there are a number of extreme events which have been plotted as stars. And then of course, you look at to your right, which is the difference of the flow duration curve between the post and the pre period. And now you can start looking at the differences. The differences are really large at many stations here. So at Bhagirathi, which is the left-hand basin here, you can see that the both low and moderate flows have significantly been altered, and the flood peaks have been attenuated by and this is mostly attributed to the hydraulic structures, which is sitting at Ateri. And then at the right-hand basin, Alaknanda, here again, we can see that there has been a very significant change in the rainfall patterns, and as well as the increase in the extreme events as well. Further downstream, when these two rivers meet and form the Ganga, we also see a lot of reservoir-induced moderate flow alterations, both in the pre-monsoon and the post-monsoon period. We also see a very significant change in the sediment, sediment flux of these rivers. You can see there are changes of the order of 120%, and then minus 30%. So upstream, there are increase in the sediment fluxes, sediment storage, and also in the downstream, again, there are changes of very, very significant changes here and so on. So what is clear in this, that both the water flux and the sediment flux of both the rivers, and both in the upstream part and in the downstream parts have changed significantly, and a lot of these can be attributed to the hydraulic structures, which are this is again just with reference to one particular structure I'm talking about. Imagine the extent of impact you are likely to see when there are the other structures which will come in place as well. Now let's focus on the second problem, which is again a very major problem of sediment dynamics in the Himalayan rivers. And here we are dealing with two very different problems. One is the problem of access. Most of the Himalayan rivers are known for a very high sediment flux in their system, and this sediment, high sediment yield or high sediment flux becomes a very major problem in many of the rivers, which is interconnected to several other problems of river dynamics, for example, the bank stability, aggradational, and hotspots, and then of course the flooding risk and so on. And this has been a known problem. They have been dealing with this for quite some time and trying to find solutions to that as well. But then there is a different problem as well. There's also a problem of extraction. There are many rivers in this country where the sand is being extracted very, very extensively, which is also called sand mining, as most of you know. And this problem of extraction of sand has a different series of problems. There are problems related to channel in season, which eventually disconnect the river longitudinally and also impact the sediment transport mechanisms and fluxes. There are problems of bed armoring, which again affect the sediment dynamics. And then, of course, there are problems related to ecology as well. And most of the hydrologists and engineers have been dealing with this problem both the problems in a very serious way. And I think we have we keep asking this question as to how to achieve a balance between the problem of access and the problem of extraction to devise an efficient sediment management strategy, for example. So let me take you through to two case studies again. One is related to the excessive problem of sediment in the system, and how do we estimate that. Now, there is a classical way of hydrological budgeting of these rivers, as we all know, which primarily is based on the sediment load data measured at different points, which are typically several hundreds of kilometers apart. And therefore, this sort of hydrological budgeting poses two very serious problems. One, that it does not account for the natural aggradation and degradation cycle in the river systems. And second, that it assumes a uniform sedimentation between the two stations, which are, as I said, several kilometers apart. So as a result of that, at most stations and most places, the sediment budget of these rivers are always overestimated because we are not taking into account the losses properly. We are not taking into account the sedimentation which is happening in between and so on. So this is the typical hydrological budgeting of a Ganga-like system, which is fed by many tributaries as it flows along. And from middle, this is the part of the lower Ganga. So this is not the entire Ganga system here, from Buxar here, and then to the Farakka barrage up here. Now, to solve this problem of the issues with the hydrological budgeting, we followed a slightly different method of using the plan-form data for sediment budgeting. And these are a sample of maps which are shown here for this part of the Lower Ganga between 1965 and 2017. There are intermediate maps as well, which have not been shown here. But what is really startling here to see how dynamic the plan-form of this kind of a river system is, and how how badly there are regions which are major accumulation of sediment which are going on through time. And as you can also see that these hotspots of aggregation, they keep on shifting through time as well. Now, we wanted to make use of this data to estimate the sediment fluxes or sediment accumulation zones up here, and therefore we mapped the channel area and the bar area of this entire system at a reach scale of 5 kilometer, and this is how the data looks like. And you can see that there are both channel form, the channel area as well as the bar area, both are very, very dynamic, in a system like that. And therefore, we also designed another index which is called the bar area to channel area ratio, and that helped us to identify the various kinds of hotspots of the siltation. So the areas where the bar area to channel area ratio remains high for a reasonable long length of time, we mark them as the hotspots of siltation. And you can see that in this stretch of something like 200 kilometers, we are looking at several hotspots of the siltation in that kind of stretch. And then we followed this work, for many hotspots by drone surveys. We actually surveyed several of the hotspots by using a drone. We created a very high resolution DEM out of them, and then we computed the average height of the bar, at a low flow season, basically. And then we used that bar height to multiply with the bar area in each reach, and then we computed the sediment volume of each scale. Now, the advantage of this method was that it gave us the estimate of the sediment volume accumulated, which we call that the extractable silt volume. We are not saying that this is the total volume of sediment in that, but this is something which is above the low flow level of the river, and therefore these are extractable silt volumes. And when we compare that data with the silt volume, which we estimate from the hydrological budgeting, and you can see how overestimated these numbers are, for example. So even though this data set is based on the same time period of 1970s to 2010, we get a very large difference in terms of the silt volume which are getting here as well. But even then, if you look at the total volume of sediment which is accumulating in this lower Ganga stretch, which is from Buxar to Farakka, we are talking about something like 2,438 million meter cubes of silt, which is equivalent to something like 500 million truckload of sediment. Each truck is about 5 meter cube of load and so on. So this is the amount, this is the quantum of sediment which are sitting in these rivers, and the rivers are totally choked. In many stretches, it looks like a sea of sand in the low flow period, and the water fluxes as well as the sediment fluxes are totally impacted. So that's the compiled data for the entire stretch, and you can now see that how the deposition area changed through time, how the bar area changed through time, and how the alluvial island areas changed through time, and so on. And we have now produced the volume of accumulation of sediments in each different stretches, and then these graphs are showing you the volume which is accumulated at each reach scale and so on. Now this kind of a data gives a very easy and a workable strategy for sediment managers, because they know where the hotspots are and where they should start. So obviously, if they have to plan a strategic dredging of the sediments from a system like this, which is like several hundreds of kilometers long, the knowledge of such hotspots of siltation obviously helps them, because they can plan the excavation and then bring some equilibrium to the river system. Now, this kind of a excessive sediment load fluxes have very serious implications, and some of these are known. Where there are several flood events, which have occurred because the river bed in such rivers are basically super elevated, and therefore they are very prone to breaching of the embankments and therefore the flooding. And one such event happened in 2008 in the Kosi River, which is one of the biggest disasters or biggest avulsion which happened in anywhere in the world of about 120 kilometers. And then it caused a very, very extensive flood in the downstream. Similar event happened in the Indus in 2010. And then, of course, a slightly similar, slightly different, event happened in Uttarakhand, where this large flux of sediments got mixed up with a high volume of water as well, and that created what is the hyper-concentrated flow, and therefore, flooded the downstream regions as well. So what I am trying to point to you is that the impact of such high excessive sediments in these systems has very important cascading hazard. They produce a cascading hazards of system, including avulsion, including severe erosion of the bed, and also, of course, the extensive flooding as well. And there are enough examples available in different different rivers in the Himalayan terrain, which have been documented in the recent studies as well. Let me then now take you to a different problem of floods, which is again Anthropocene related. We've been looking at a major tributary of the Ganga, which is called Ghagra River, and looking at how the flood behavior in this system has been modified by the anthropogenic interventions, etc., and so on. So this is, as I said, is one of the largest tributary of the Ganga, and this has been suffering from chronic flood history in the recent decades, and so on and so on. So what we are looking at a complete hydrological analysis of these rivers. We created the flow duration curves of these rivers, both in terms of discharge and also the sediments. We now know that there are how the sediment flux varied through time. We have also been looking at the flood characteristics of these rivers by using some of the indices which we designed earlier. And we know that there are very large discharge variability in the Ghagra, for example, compared to another tributary which is called Sharda here. So Ghagra, this whole system is fed by two rivers. One is a Sharda coming from the west, and then there's a Ghagra, which is also called Karnali in the Nepal region, which is coming from the eastern part of the catchment here. And we have data from several of these outlets, which you can see here, and of course other points as well. But right now we are trying to show you the hydrological data analysis for these four major outlets at these rivers. And you can also see how the catchment sizes are different for each of these outlets, and that eventually reflects in the flow duration curves of these tributaries as well. What we experienced while working on this river was that, yes, there are standard ways of analyzing the hydrology here using the water level and discharge data. We always do this flood frequency analysis using flood frequency, using discharge data and so on. But and that curves look pretty nice, the standard relationship between the water level and the discharge. But when you start looking at the river and the hydrology more closely, you realize that there are many places where the water level and the discharge, they don't really correspond to each other at all. And that is because, again, there is a huge flux, huge impact of the geomorphology in terms of the cross-sectional area, and also the sediment flux, which is playing a role here. You can see here how the cross-section of this river at a particular station has been changing through time. This means that the channel morphology at several points where the hydrological data is being collected is drastically changing through time, and therefore, if you are not calibrating the discharge accordingly, your discharge data may be quite erroneous. But fortunately enough, the water level data seems to be more accurate, and therefore we decided to use the water level data, which is also called stage, for a stage frequency analysis. And this is what we have shown here. The advantage of the stage-based frequency analysis is that it is not so much influenced by the cross-sectional change, because the water level will change even if the cross-sectional area is changing, and it is also reflecting the impact of the riverbed changes as well. So we have been pursuing this work, At this time, we have calculated the different frequencies of the stage, and we are relating that to the flood risk, etc., and so on. The one very quick advantage with the stage level frequency data gave us that it allowed us to, to create, a very high resolution flood risk maps for different locations, because and that we did by again using the drone based mapping. We created high resolution topography of the floodplain and also the channel bed, and then we related that to the stage frequency analysis, and we created something like a 10-year flood depth map and the 50-year flood depth map and the 100-year flood depth map. Now, this kind of localized high resolution, flood risk maps, they become very useful because these are the areas where a very large and a very dense population actually lives, and therefore, and more so because this is taking into account the riverbed elevation changes and also the floodplain topography. In the same context, I would also like to highlight another study which again highlights the role of the dynamic flood topography on the flood inundation. This is a work by Hugh Sinclair and Julie Dingle at Glasgow, and they looked at the upper part of the Karnali, the same Ghagra River, and they actually established many things. They looked at how, for example, a better representation of the channel geometry can affect the flood inundation map, and they showed an increase of about 14% in terms of what kind of a data set they are using. They also observed, for example, how a better dam can give you a better representation of the floodplain topography and therefore a more accurate inundation pattern. So again, they found some change up here, and then of course, there are other issues of minor resampling effects and so on. Now, this study again showed how the accurate representation and high resolution data of the channel and floodplain topography can improve the flood risk estimation. Again, some more data from the same paper, which looked at how the impact of channel in season aggregation will impact the flood inundation pattern, and then how the impact of flow switching, because again, these are multi-channel system, gridded channels, and the flow keeps on switching from one channel to the other. And if you are not taking that into account, you're again wrongly estimating the flood risk and so on. So what these two studies are basically suggesting that in such kind of a mobile river system, when you are trying to develop a hydrodynamic model, you must have a very strong field data, and that is where high resolution data from the UV, the ADCP, channel bathymetry, and floodplain topography, all of them come into picture. And all of them, as we know, are very strongly impacted by the anthropogenic activities, including siltation, for example. And this obviously has a very strong implication for floodplain inundation, particularly in the alluvial reaches where there is a large population living and they are at risk, for example. So this is basically what I was trying to convey here. Now let's move on to the next topic for today, and that is the reverse of that, which is basically where the sand is being removed. And again, sand mining is a very serious problem in most of the Indian rivers, not just the Himalayan rivers, but also in the southern rivers, southern Indian rivers as well, the peninsular ones. So we have initiated a study on one of the small Himalayan river, and we are trying to understand how do we understand the morphological response of the river to sand mining at reach scale? How do we estimate the volume of sand which is being extracted? How do we understand the sediment connectivity which is getting impacted? And then how do we assess the larger impacts of river system, for example, and how do we build a process response framework, for example? And then, of course, we are trying to suggest solutions as well as to how to ultimately reduce the impact of these as well. So very quickly running through this case study again, we looked at the planform changes of these different stretches. This is a small stretch of that river, and you can see how dynamic the whole system has been. And most of the changes are, we are now sure about this, are related to the sand mining effect. This is a total of about 33-kilometer stretch of a river which is being mined, continuously. There's no gap in between. There's a huge loss of bars and wet channels. which you can see between 1994 and 2020. There's a loss of breeding, sinuosity. So there's a complete transformation of a river, as you can see from this map. This is a small stretch of a river, which I'm trying to show you for the sake of clarity, but we have done the mapping of the entire 33-kilometer reaches as well. We then wanted to look at, we then analyzed this morphological data in terms of the different platform parameters, and then we again see, there are this very sharp reduction in the channel belt width. There's there are different kinds of scenarios. There are also lots of geomorphic features and so on. Now, the idea is that we would now like to convert some of these indices to characterize the morphological impacts on the river system because of the sand mining. That work is still going on. But then meanwhile, we also had another task at hand, and that was to look at some of the major hotspots in high resolution, and we again used drones to capture the morphological parameters of these features, and you can now see how how badly these rivers are being mined. You can see several patterns, several in-channel mining, loss of geomorphic features. There are thalweg shifts. There are tailing ponds. There is a complete loss of the habitat in these regions. It's totally dry for most of the period as well, and so on. So this is how, in fact, the right-hand side picture actually tells you this is a picture of a river bed. And you can imagine there are hundreds of trucks lying around here and literally mining the entire river bed. At least 4 to 5 meters of incision created by the humans themselves. That's a serious issue here. Similar issues here in another stretch. And now what we did in this work, that we actually flew the drone before the mining started and after the mining was completed. So we have 2-time data of a very high resolution dam, and there are some representative longitudinal profile I'm trying to show you here, which shows how drastic the changes are at places. There are 10 meters of incision we are looking at. There are 14 meters of incision we are looking at here, and on average you can see that there are at least 5 to 6 meters of incision in a stretch like that. Okay, so that is huge. You can then convert. We are now trying to convert this this difference of dam into the volume of sand which is being extracted in 1 year. Just 1 year you are looking at. So you're looking at 1 year data, pre-mining and the post-mining, and you're looking at 6, 10, 14 meters of incision in stretches like that. So this is a huge impact we are looking at in a system like that. We then, are trying to set up a model which is called Cascade, which is trying to assess the connectivity and sediment fluxes. I will have to skip some of the details here because I think I'm running out of time. But then this model, basically looks at the grain size data, the river morphological data, and many other parameters to set up the model. And what this model is showing us, how is the pre and the post mining scenarios are changing in terms of the sediment transport processes. So this is one of the reads which I have shown here, and which is showing how between the pre and the post mining period, how the sediment is being entrained, how the sand and gravel size particles are being entrained and in the pre mining period, and what happens in the post mining period as well. So what is apparent here, that the sediment distribution at reach scale is changing very, very significantly in the pre and the post mining period. This is one example. This is another reach here which is further downstream, and again we see here that so the last stretch was the stretch which was dominated by the entrainment process. This is the stretch which is dominated by the deposition process here, and again you see a very large scale changes in terms of sediment sources, sediment fluxes, and connectivity structures, and so on. This is just 1 year of simulation which we are looking at, and then we plot at a network scale. We look at the pre-mining and the post-mining scenarios. We are now trying to look for correspondence between the cascade modeling results and the platform results, and then eventually run this model on a yearly scale to identify the hotspots of erosion and degradation and so on. So this is what we are trying to do. As of now, we have built a conceptual process response framework. We are looking at a platform dynamics, which are primarily being manifested in terms of in season. We run the cascade model, and then we are looking at the feedback of each of these parameters in terms of bed armoring, sediment load available, and then longitudinal connectivity, and then the erosion. So how these different processes are being connected, this is the kind of a model which we are trying to develop here. And there are some stock examples which you can see right here. This is the bridge, which is the entire base of the bridge is has been exposed. This is posing a huge danger to the stability of the bridge as well. This river bed was supposed to be somewhere here at some point of time, and you can see that entire area has been scoured because of the incision by the river, and of course mostly caused by these sand mining, etc., and so on. So these two problems are quite distinct, and they both have their own implications. Himalayan rivers are sediment charged. There are huge amounts of aggregation going on in many places. The strategic extraction is required to maintain the sediment regime, but if you do that extraction beyond a certain threshold, beyond a certain limit, it becomes disastrous. And that is where a proper sediment management strategy is required for rivers like that. There are policies, but then there are issues about implementation and the political will to do that. So far, okay. Now let's move to a slightly different problem of river health assessment of the Indian rivers. River health is a very broad term, and what we are looking at is that how good or bad the river is in terms of the function it is supposed to perform. And these functions are many: the flow of water, the biota, the fluxes, morphological health, and all of that. As a geomorphologist, I am looking at several parameters to design in terms of indicators of the geomorphic health of the system. We are not looking at the ecology and water quality and other aspects. They are all equally important, but we are primarily looking at the geomorphic health of the system. What we do is that we are first designing a criteria to designate what is called as a river space or river corridor in many European European literature. We define the active floodplain and the valley margin as a river space, and we would like to design specific criteria for the permissible use of this space. So we did this work for the entire Ganga system. We delineated the river space for the entire region, and the observation is that it's quite variable. The river space is quite variable from the upstream to downstream. There are sometimes a very large part of the valley margin is occupied by the floodplain itself. There are regions which large alluvial island. There are regions which are confluence bars. So there's a huge kind of geomorphic diversity you are looking at in a river system like Ganga, for example. So the first task which we did was to classify the entire Ganga River in terms of its geomorphological diversity. We used a nested hierarchical approach in terms of landscape setting, in terms of channel confinement, in terms of floodplain confinement, channel morphology, and then we divided the entire river into 10 different geomorphic classes. And each of these classes were unique in terms of their morphology and in terms of their processes, for example. Once we did that, we then designed we have then designed a series of river health related parameters, mostly geomorphological parameters, which are well known. So we use sinuosity, bread channel ratios, occupancy. We have designed the index for floodplain development, and then of course we use the standard parameters like stream power, and then we integrate each of these parameters in a GIS framework, designing a decision factor matrix using what we call as an analytical hierarchical approach, and then we integrate all of these parameters to design what we call as a river health index. Again, emphasizing that these are primarily geomorphic river health index we are talking about. So this kind of integration of the different parameters, although it has some subjectivity, but there are ways of removing the subjectivity and creating a more accurate assessment. We came up with the river classes or river health classes of the entire stretch of the Ganga from the upstream to downstream. Just to note that we use a slightly different decision matrix for the mountainous reaches and the alluvial reaches, because we understand that the processes which are operating in the mountainous parts are slightly different from the alluvial reaches. There is a dominance of controlling factors, for example, stream power and connectivity in the mountainous reaches, whereas the alluvial reaches are more prominent in terms of the landform dynamics, development, and occupancy. And therefore, we change the weightage factors of these different factors, for the mountainous reaches and the alluvial reaches to come up with the river health assessment and so on. So then when we plotted the scores of the river health along with the geomorphic characterization which we had done earlier, we find that there's a very nice correlation between the geomorphic form and the RHI classes, which is expected anyway, because these indices are also derived from the geomorphology. We found that most of the mountains reaches have much better health conditions than, including, even though there are several interventions there, they're still maintaining a reasonably good health. The moment the river reach comes down to the alluvial part, the RHI values typically drops, particularly around the interventions, but they do pick up again. There are reaches which are pretty bad in terms of river health. For example, around Allahabad here, for example, and then there are, as you can see, there are several tributaries which are joining the Ganga at many points, and at each of these points, you can see that the river health actually improves quite significantly. So the additional discharges which are adding, the river, that obviously helps to improve the river health, both in terms of channel morphology and also hydrology. Now, these are just some random examples of the river health of the Ganga in many parts. There are many examples, but I've just picked up a few. There are massive urbanization around Haridwar, which is upstream reaches of the river. There's a very major channel modification around the Narora Barrage, which was set up, sometime around 1955-56, and then the river is now changed quite drastically. There are major geomorphic changes around Kanpur, for example. And then, of course, don't forget that there's a huge population explosion which is happening in many parts of the Ganga basin as well. And these are, again, comparison between 1976 and 2008. And all these red patches here are basically showing you the urban areas which we mapped in different parts of the window as well. So obviously, the engineering interventions, the barrages and dams, for example, the urban expansion, and the LULC changes, all of them have impacted the river system like Ganga in a very major way, and that has led to a serious degradation of the river health of this river, this very important river. To conclude, we have understood, we have documented that the human interventions have played a very important role in terms of modifying the flow and sediment flux in these rivers. And in terms of sediment, both access and extraction of sediments are posing a serious problem to the river. There are increased flood risk because of super elevation. There are sand mining issues which are impacting the river morphology and sediment dynamics in a very major way. But we can, and then of course we can use several of these geomorphic parameters to provide a very quick assessment of the river health. And therefore, we argue that such kind of geomorphic assessment can be incorporated in the river rehabilitation strategies as soon as possible. So finally, this entire work has been supported by many funding agencies, most importantly the National Mission on Clean Ganga, the Water Resource Department of Government of Bihar, the Ministry of Education, Government of India, and of course several students from whose work I have borrowed very freely. So all of the students have contributed significantly to this work. So just to leave you with this slide here, this is a kind of an atlas we designed some time ago. We call this as a Ganga of the past. You can find this atlas as a file in this link up here, and you can see how the Ganga looked like in 1960s and now. We have used we have 10 different windows which we selected, and for each of the windows we analyzed the platform changes, the land use land cover changes, and of course we have put in a lot of anthropogenic data as well, and to guess, for this is designed for a common man to understand how a river system like Ganga has changed through time, and how we can help to restore the whole system as well. So I'll stop here for today, and it has been a pleasure giving this lecture, and I'll be more than happy to answer a few questions. I pitched all there. Thank you so much for the invitation again.
Thank you. Thank you very much, Rashid, for this excellent holistic presentation that you have been showing us all these different approaches, how we have to study rivers, how you have to integrate all this data. Please, for the public, write your questions so we can answer your questions, right? You have to write the questions in the chat. We have one of the participants asking you to elaborate a little more on how you work together with ecologists, for example, and how to integrate this data with the protection of the aquatic biodiversity and this kind of plants. Maybe you can tell a little more about that.
Yeah, I have not worked on the ecology part per se, but then we work very closely with them, and the idea was to demonstrate that there is a strong link between the river morphology and the biotic diversity. So we actually are finishing that work now, and we have found that there is a very close correspondence between the morphological changes and the biodiversity loss. I have not been able to show that data in the talk today, but I can tell you that there is a very strong correlation between the two. See, it's basically a question of semantics. What we call as the morphological elements, they call that as habitat. Okay, so if there is a loss of the morphological elements of any river, it is bound to create a loss of the habitat for them as well. So there is a very strong, theoretical connection, but this has to be demonstrated, and we are working on that as well. Thank you.
Thank you, Rashid. Do we have more questions? Question, please. Let's wait. Somebody probably is writing some questions.
Yeah, there are some Portuguese questions as well. There are questions in Portuguese as
well. Of course, I deeply know your work and all this kind of result that you are producing, but I think that there is a strong message here. We are trying to disseminate the similar message here in our region. And what you show us is how you can contribute and attack to different problems, multidisciplinary problems, very, very clear applied issues about river management. But you need the strong knowledge about fluvial geomorphology, morphodynamics, good mapping, and a lot of fieldwork. And why I emphasize this in your presentation, Rashid, because you know very well we have been teaching for a long time. More and more we have people prone just to, okay, we're going to model, how you shown here. I'm going to apply a hydrological modeling, boom, and I resolve all the floods. Or, let's do a sediment budget using 2D plan view balance without introducing all the sedimentology, the volumes, the mobility of the bars, and so on. And another particular interesting result that you presented here is about the wealth of the river, right? How healthy the river can be. And this is important because, for example, here in Brazil, many people just may focus on, okay, river quality is the hydrochemistry, the biological aspects. And you are showing us how important are the hydrophysical aspects to understand if a river is healthy or not, right? I think it's very innovative and very important, this message.
Yeah, I think the important message is that, the other parameters of river health, for example, the water quality, and to some extent the biological diversity, they are not so difficult to correct, remember, okay? But if a river has changed the morphology, in a drastic way, it will take a huge time to recover. So the recovery from the water quality problems and the biodiversity loss is much quicker, but a recovery from a geomorphological transition or geomorphological loss is much longer. So therefore, if you look at the different kinds of threshold, the biotic thresholds and the geomorphic threshold, the geomorphic threshold is actually very high. So returning from a geomorphic, loss and recovery is very, very hard, and therefore we have to make sure that the rivers do not cross that threshold. Otherwise, it's almost impossible to rehabilitate or restore that kind of a river. So that's an important message. I think everybody has to understand that.
Thank you. Well, since that we don't have additional questions by the public, so we can keep talking, for hours with you. But seems that it's more relevant to know that, so the public have some additional questions. I would like to thank you again, Rashid, for all this beautiful presentation. Thank you very much. Right, and you always are welcome here in Brazil. And in the name of the organizing committee, thank you again for joining us.
Thank you so much for inviting me. It was a pleasure. Thank you.
Thank you. Thank you very much to everybody. Bye-bye.